counterclockwise spiraling of lightning strike damage observed on trees can be attributed to the Coriolis effect. The Coriolis effect is a phenomenon that deflects moving objects to the right in the Northern Hemisphere and to the left in the Southern Hemisphere, a consequence of Earth's rotation. As lightning discharges onto a tree, its path follows the trunk. The Coriolis effect subtly influences this path, causing a deflection. In the Northern Hemisphere, where Portage, Indiana is located, this deflection is to the right relative to the direction of the lightning's travel. This deflection doesn't create a perfectly straight line, but rather a spiral. The lightning's energy seeks the path of least resistance down the tree. But as it does, the Coriolis force imparts a slight lateral movement. The cumulative effect over the length of the tree trunk results in a visible counterclockwise spiral pattern of damage. It's important to note that this is a subtle effect. Other factors such as the tree's internal structure, moisture content, and the precise angle of the initial lightning strike also play significant roles in determining the exact path the electricity takes. However, the Coriolis effect provides a reasonable explanation for the consistent counterclockwise spiraling observed in multiple trees. The fact that multiple trees exhibited counterclockwise spirals further supports this explanation, as the Coriolis effect would consistently act in the same direction within a localized area in the Northern Hemisphere. It's not just lightning that is affected by the Coriolis effect. Large-scale weather patterns such as hurricanes and ocean currents also exhibit rotational behavior influenced by this phenomenon. Hurricanes rotate counterclockwise in the Northern Hemisphere and clockwise in the Southern Hemisphere, a direct result of the Coriolis force. Similarly, major ocean currents are deflected by the Coriolis effect, influencing global heat distribution and climate patterns. The strength of the Coriolis effect depends on the latitude and the speed of the moving object. It is strongest at the poles and weakest at the equator. The faster an object moves, the greater the Coriolis deflection. While the speed of lightning is extremely high, the effect is still subtle due to the relatively short distance the lightning travels along the tree trunk. The internal structure of the tree itself also plays a role in the path the lightning takes. Wood grain, knots, and areas of higher moisture content can all influence the direction of the electrical discharge. These factors can sometimes override the Coriolis effect, leading to variations in the spiral pattern or even a lack of a spiral altogether. To understand the relationship between lightning and trees, it is important to first understand what lightning is. Lightning is a sudden electrostatic discharge that occurs during an electrical storm. This discharge occurs between electrically charged regions within clouds, between clouds, or between a cloud and the ground. Lightning is initiated by a step leader, a channel of ionized air that propagates downwards from the cloud in discrete steps. As the step leader approaches the ground, it induces an opposite charge in the ground, which then sends up a streamer to meet the leader. When these two channels connect, a large current flows, creating the bright flash of lightning that we see. When lightning strikes a tree, the electrical current travels through the tree, often following the path of least resistance through the sapwood, which contains a high amount of water. The rapid heating of the water in the sapwood causes it to vaporize, creating a pressure wave that can explode the bark and wood of the tree. This is what causes the characteristic scarring and splintering that we see on trees that have been struck by lightning. The extent of the damage depends on several factors, including the strength of the lightning strike, the type of tree, and the moisture content of the tree. Trees with high moisture content are more likely to be damaged by lightning because the water in the tree provides a conductive path for the electrical current. The type of tree also affects the likelihood of lightning damage. Trees with deep roots are more likely to be struck by lightning because they are more likely to be grounded. Tall, isolated trees are also more likely to be struck by lightning because they provide a direct path for the electrical current to reach the ground. The damage caused by lightning strikes can weaken trees, making them more susceptible to disease and insect infestation. Lightning strikes can also kill trees outright, especially if the strike is strong enough to completely destroy the tree's vascular system. The spiral pattern that lightning creates on trees is not always counterclockwise. In some cases, the spiral may be clockwise or even irregular. This is because the path of the lightning is influenced by a variety of factors, including the tree's internal structure, the moisture content of the tree, and the angle of the lightning strike. However, the Coriolis effect does play a role in the overall pattern of lightning strikes, and it is likely that the Coriolis effect is responsible for the counterclockwise spiral that was observed in the trees. While the Coriolis effect is a plausible explanation, it is also important to consider other factors that could contribute to the spiral pattern. Firstly, the structure of the tree itself. The grain of the wood, the presence of knots, and other irregularities can all influence the path of the lightning. If the tree has a natural twist or spiral in its grain, this could guide the lightning in a particular direction. Secondly, the moisture content of the tree. Water is a good conductor of electricity, so the lightning will tend to follow the path of least resistance through the wettest parts of the tree. If the moisture is distributed unevenly, this could create a spiral pattern. Thirdly, the angle of the lightning strike. If the lightning strikes the tree at an angle, this could cause it to spiral down the trunk. Also, consider the surrounding environment, proximity to other objects such as electrical towers, etc. While the Coriolis effect is a factor in large weather events like hurricanes, the idea that it would create visible and consistent spiraling on trees struck by lightning is not widely accepted.